Dimensions. First, a scalar is just a number. More technically, a scalar is a mathematical object which can be added, subtracted, multiplied and divided, or, colloquially, a number. Note that scalars are denoted by italic letters. Formally, a scalar is a mathematical field, that is a set of objects which can be added and multiplied with certain properties. Addition and multiplication are closed on scalars. Any two scalars can be added or multiplied, returning a scalar. These operations can be done in any order without changing the result. They have an identity element. A scalar and an identity returns the same scalar. The additive identity is usually denoted by 0, and the multiplicative identity by 1. Every scalar has an additive inverse, and every scalar except 0 has a multiplicative inverse. Multiplication distributes over addition. Rational numbers, real numbers, and complex numbers are examples of scalars. A vector is usually called a direction or displacement, but actually a vector is just an object that can be added, multiplied by a scalar, and a few other operations. Note that vectors are denoted by bold letters. Formally, a vector is a mathematical object which has the operations of adding vectors and multiplying a scalar and vector. The additions can be done in any order without changing the result. The vector addition has an identity usually denoted by 0, and scalar multiplication has an identity usually denoted by 1. Every vector has an additive inverse. Scalar multiplication distributes over vector and scalar addition. What the vector represents is not important as long as the operations of adding vectors and multiplying a vector by a scalar make sense. A vector could be a number, a matrix, a function, a tensor, or years. A vector could not be a year number. It makes sense to talk about 3 years, or 3 times 1 year, or 1 year plus 2 years, but it does not make sense to talk about twice 1969 or 2020 plus 1066. A zero vector is a special vector that can be added to any other vector without changing it. X plus 0 is equal to x. A linear combination of vectors is a sum of individual vectors each time a scalar. Any vector can be expressed as a linear combination of other vectors. This sounds like a vector is defined in terms of a vector, which seems evasive, but this actually is the case and turns out to be part of the power of vectors, and this explains what a dimension is in mathematics. A linear equation is a linear combination equated to a zero vector. An equation in one variable has a graph which is a parallel to one the axes. An equation of two variables is a line. An equation of three variables is a plane. An affine equation is a linear combination equated to a non-zero vector. In this case, the vector is called a constant to mean it does not change while we are considering a particular equation. In a sense, a constant is a very stubborn variable. As an example of a set of data that can be represented using vectors, consider this small sextet of friends. Each person has 5 numerical attributes: P, Q, R, S, and T. As presented, no apparent relation exists among the attributes. A supposed relation like Q is always twice P would allow the Q column to be dropped, making the table smaller without losing any information. A simple kind of relation would be where attribute can be expressed as a linear combination of other attributes. Such an attribute is said to be linearly dependent on the other attributes. Attributes which are not linearly independent. Gaussian elimination is a process to modify tables to reveal where the sum properties are linear combinations. Gaussian elimination has other uses, but this is how it will be used here. Gaussian elimination is repeated application of 3 rules to convert the table into a form where the diagonal attributes are all 1. It is also 0 in the lower left, and any non-zero entries are in the upper left. The rules are to exchange 2 rows, multiple each attribute in a row by a scalar, and add the scalar multiple of one row to another. These rules preserve the linear relations while simplifying the table. Those columns which have the leading non-zero value in one of the rows mark those attributes which are linearly independent of other attributes. The other columns are a linear combination. P, Q, and R are independent attributes in this example. S and T are dependent attributes, and we can read the relations off of the final reduced table. With this data, two linear relations have been discovered. Are there other relations? Because we do not have a mechanical way to discover relations in a mass of data, relations can go years before being discovered. The Gaussian elimination used before is one trick. However, many relations in nature are not linear combinations. Another relation that often occurs is a product of powers of variables, such as Newton's gravity, potential difference equals current times resistance, or power equals current times potential difference, and equivalently power is potential squared divided by resistance. Without going into details, the logarithm operation converts multiplication into addition and exponentiation into multiplication. This converts formulas of products into linear combinations. This is sometimes done by plotting data on log-linear or log-log graphs that can turn such relations into recognizable linear relations. For example, take the logarithms of the attributes of the sextet. We then do Gaussian elimination of the attribute logarithms. Log P and log Q are independent attributes in this example. Log R is a dependent attribute. Because T is defined in terms of R, this is rewritten with R as the independent attribute. Gaussian elimination can be used for other purposes. An augmented matrix is a matrix with additional columns usually marked with a vertical line. The extra columns participate in the row edits, but the elimination stops before the augmented columns. This example shows how to compute an inverted matrix. Put the original matrix on the left and the identity matrix as the augmentation. If the elimination results in an identity matrix on the left, the matrix is invertible and the inverted matrix is the augmentation. Let us go back to only consider linear combinations. Then with this sextet we are left with three irreducible, independent attributes, P, Q, and R. I chose which attributes were left. I could have chosen P, Q, and S, or T, Q, and S, or even had made up new attributes with which to define the others in linear combinations, but the minimum and maximum number of independent attributes needed to describe everything will be 3. The number of independent vectors needed to express every vector as a linear combination is the dimension of the vector space. The dimension of the sextet is 3. To keep the numbers smaller, I will use P, R, and S as the independent vectors. This is called three-dimensional, and the three attributes I chose are called the basis vectors. I can change which attributes are basis vectors, but I will always need exactly 3 to completely describe the data. That is really all a dimension is. Each person equals a linear combination of the basis vectors. When the basis vectors are understood, just the scalar multipliers can be listed as coordinates. The definition of linear combination and linearly independent are formalized. A linear combination is the vector sum of scalar multipliers of vector. Note that due to closure any linear combination is a vector. Vectors are linearly independent when none of the vectors can cancel out the others. The only way to cancel out any element is to zero out all the elements. In particular, when a set of vectors are linearly dependent, at least one of the vectors is linear combination of the rest. A span space is all the vectors which can be a linear combination of the spanning set. It is not required the spanning set is linearly independent or that the linear combinations are unique. The span covers the space with allowed duplicates. All vector spaces have a spanning set, but the proof involves infinitely dimensional space, which is a topic I am going to skip until later. For now I am only dealing with vector spaces with a finite spanning set. The n-dimensional set of reals is an example of such a span set. I say this to ensure I am talking about an actual object. A basis of space has two requirements. Every vector in the space is a linear combination of the basis, and the basis is linearly independent, making the basis minimal in a sense. In mathematics, a definition does not imply existence. We also need to prove that the finite vector spaces under consideration actually have a basis. This definition and theorem 3 do not imply any relation between different bases. This lemma gives a numerical relation between a set of linearly independent vectors and a spanning. In a sense, informally speaking, the independent set lacks duplicates and can have holes, and so is no larger than a spanning set which allows duplicates and avoids holes. The lemma element by element replaces an element of the spanning set with the independent set, ending up with original independent set augmented with enough elements of the spanning set to cover any holes. The relation when the spanning set is also linearly independent, thus a basis, is handled by the next theorem. By the previous theorem, all bases have a kind of symmetry that means they all have the same size. Thus we finally proved that all bases have the same size, as asserted previously. This theorem combined with the dimensions theorem ensures for each basis, we have unique list of coordinates with respect to a basis, and the coordinate list length is the same with any basis. In nature, we need 4 dimensions to describe position of an object, 1 time dimension and 3 space dimensions. While these space-time dimensions are what are usually known as dimensions, more information can be additional dimensions. To describe the trajectory of an object, we need 7 dimensions for time, space, and velocity or momentum. The momentum provides the direction of motion as well how objects interact when they collide. We need the energy and mass. Because one can be defined in terms of the other, we only need one. The last attribute added is electric charge, and with the Coulomb's 27's law as charges attract and repel, that makes object 9-dimensional. We can reduce the number of dimensions of the results with a projection. For example, we can replace independent attributes P, R, and S with a weighted average. A projection can summarize the vector while losing some of the details. This projection summarizes each vector with one number, but we can no longer distinguish Alan and Diane. A mathematical projection is not the same as a movie projection. A movie projection converts a 2-dimensional film frame to a 2-dimensional screen. It is however the same as a camera which projects a 3-dimensional scene into a 2-dimensional film frame. Each of our eyes also projects a 3-dimensional world onto a 2-dimensional retina. A projection loses information. Mathematical operations in general either reversibly transform information, with no loss, or transform a larger set into a smaller set, with some loss of information. We cannot recreate a 3-dimensional space from a 1-dimensional projection alone. Any additional attributes would have to be defined in terms of the one existing attribute, and thus reduced back to 1 dimension. We would need some way to create new information. A Euclidean vector is a traditional vector, a list of numbers which is a length and a direction. A Euclidean vector is usually shown as a directed line segment with one end at the origin. The angle between the vector and coordinate axes shows the direction, and the distance between the ends is the length. While a Euclidean vector is usually drawn with one end at the origin, the actual position of the vector is not relevant, only the length and direction. Move a copy of each vector to the end of the other vector. The shape of all 4 line segments is a parallelogram lying in one plane. This geometric manipulation coincides with the addition of Euclidean vectors. Move the beginning of one vector to the end of the second, then add the vector from the beginning of the first vector to the end of the second vector. Scalar multiplication changes the length of the vector without changing the direction. Reversing the direction on the same line is multiplication by a negative scalar. A zero Euclidean vector is a vector of length 0. A zero vector can be regarded as pointing in any direction or no direction. While vectors are often drawn with one end at the origin, Euclidean vectors are not associated with any one point. A vector can be drawn at any point without changing the vector. Norm is an operation defined on some vectors which introduces the idea of distance. The norm of a Euclidean vector is the length of the vector. It can be useful for other vector spaces to distinguish vectors with norm 0 or 1 or other. The inner product is another operation which introduces the notion of an angle between two vectors. The inner product of two Euclidean vectors is a multiple of the cosine of the angle between the vectors. Again, it can be useful for other vector spaces to distinguish vectors which are parallel or at right angles. A vector space has no intrinsic geometry associated with it, but to norm and inner product have some notion of distance and angular separation on which to build a geometry. This joins algebraic mathematics to geometric mathematics. The inner product of a Euclidean vector is called the dot product or scalar product. It is the sum of the element-wise products of the vectors. Two theorems deal with multiplying vectors by zero, which not surprisingly results in the zero vector. The Cauchy-Schwarz, Cauchy-Bieniawkowski-Schwarz, or Bieniawkowski-Schwarz inequality is, quote, a useful inequality encountered in many different settings. It proves a relation between inner products and norms. When a vector space has an inner product, the inner product can be used to define a norm. A vector space can have a norm without an inner product, or an inner product and unrelated norm. First, an inner product derived norm is defined. It is then proven this satisfies the axioms of a norm. First, use Cauchy-Schwarz to prove the triangle inequality. This complicated because up to now norms and inner products do not have an obvious relation. Cauchy-Schwarz involves multiplying norms, so addition has to be turned into multiplication. The second norm axiom comes straightforwardly from inner product scalar associativity. The last norm axiom is just a simpler case of the inner product positive definite axioms. This concludes that when a vector space, it can be used as a norm. The law of cosines is a generalization of the Pythagorean theorem. While the Pythagorean theorem is restricted to right triangles, the law of cosines allows triangles with any interior angle. This is proven in three parts: for obtuse angles, acute angles, and right angles. This is proposition 12 from Book 2 Euclid's Elements. Euclid did not know about cosine, instead stating it as ratios of rectangles derived from the triangles. A right triangle is constructed on the original triangle so that the Pythagorean theorem can be used. Then, using the square of sums formula, the parts of the constructed triangle are related to the original. This is proposition 13 from Book 2 Euclid's Elements, again updated to use cosine. A right triangle is constructed this time inside the original triangle so that the Pythagorean theorem can again be used. Instead of square of sums, the common factors are recognized and substituted. The Pythagorean theorem is the law cosines for right angles. The cosine term can be added because it is zero for right angles. This proves the law for all triangles. Given two vectors with the same origin, they form two sides of a triangle with their difference at a different origin as a third side. This gives us a triangle, and the law of cosines gives the angle between the vectors in terms of the original vector and their difference. The difference is then removed with a bit of algebra. This theorem requires the dot product and Euclidean vectors and does not apply to vectors in general. While other vector spaces might not have anything that can be meaningful called an angle, it can still be useful to think of vectors as orthogonal or parallel. This allows generalizing the notion of orthonormal and defining an orthonormal basis. When we put a Euclidean vector at the origin, we can identify the vector by measuring the endpoint against the axes. Suppose we have a set of Euclidean vectors each length 1 which lie on each axis. Then instead of measuring a vector against the axes, we can measure it against this set of vectors. Because this set of vectors is orthonormal, the length of another vector compared to each is simply the inner product of the two vectors. This greatly simplifies computing coordinates. The set of vectors that can take the place of the axes is called the basis of the space spanned by the axes. The spaces does not have to be oriented the same as the original axes. This allows us to replace the vague references to axes and measurement against them to a precise definition in terms of basis vectors. A basis is the smallest set of linearly independent vectors which can express every other vector in the space in a linear combination. The coordinates can be computed with the inner product when the basis is orthogonal. Otherwise, the coordinates are solutions of linear equations. The number of vectors in a basis is the number of dimensions. The basis vectors are placed in an order. The exact order is not important, just that the same order is always used, and the coordinates are in the same order expressed as an ordered n-tuple. The vector is a linear combination of the coordinates and basis vectors. The basis is not usually referred to directly as long as it is clear what the basis is, and the coordinates are used instead. While the basis vectors can match the original axes, the basis can be located anywhere and point in any direction as long as they point in enough different directions that any vector can be described by them. Because vectors can be used in linear combinations, I can use Gaussian elimination for a list of vectors to determine how many dimensions are needed. The number of dimensions can be less than the number of coordinates. This is a two-dimensional vector space with all the vectors in a plane. The green vectors are used as the basis. Because this is not an orthonormal basis, we have to solve simultaneous linear equations, Gaussian elimination of augmented matrix, instead of simply taking the inner products. The basis vectors are columns of the matrix, and the solved for vectors are the augmented columns. The reduced matrix shows the coordinates. A vector can be represented by a list of scalars which are a shorthand for a linear combination of implied basis vectors. The vector is intended to be an abstraction rather than just a list of coordinates. Operations on the vector produce the same result regardless of the basis or coordinates. Numerical coordinates are needed to compute the application of a function to the vector. We can compute the same coordinates with a change of basis. This is done by applying inverse of the function to the basis and computing the coordinates of the original vector in the new basis. In a sense, the dimensionality of a space is how complicated each element of the space is or how compactly it can be uniquely described. Heretofore, the elements of a space can be uniquely identified in a finite number of dimensions. Can we have space where every element is so complex that each element requires an infinitely long unique identification? Yes. A common case is functions. At their most abstract, a function is just a collection of ordered pairs subject to a few rules. Two functions might differ in just one ordered pair, but any one ordered pair among the infinite number of ordered pairs. Because of that, it might take a separate piece of information from every single one of the infinite ordered pairs to uniquely distinguish each function from all the others, and this means infinite dimensions. The next question is whether a space has a basis. Finite dimension spaces have a finite basis. Families of functions can be infinite bases which have some rule to specify each basis function. Two families in particular are the Taylor series and the Fourier series. The Taylor series can be defined for a function that an infinite number of derivatives at a point, or function whose derivatives become zero. The Fourier series is defined on functions which are defined between an upper and lower limit. The Taylor series was an early way to generate an infinite sum, a linear combination limit, of a scalar times basis function. It was introduced by Brooke Taylor in 1715. Other families of functions can also be used, such as Chebyshev polynomials. The basis functions of the Taylor are powers of x divided by a factorial, and the coordinates for this basis are the derivatives all evaluated at the same place. One of the requirements is that the functions can be differentiated at that interval as many times as necessary. The Taylor series produced many useful function approximations. However, the basis functions are not orthogonal, and it depends on evaluating at one point. The further from that point, the less accurate the approximation. The Fourier series uses orthonormal functions as its basis functions. This makes each coordinate depend on only one basis. As the coordinates are based on an entire interval, the approximation is accurate over that interval. Related topics are degrees of freedom and independent versus dependent variables. When you are looking at a problem, such as what is the reach of a robotic arm, this depends on how many joints and twistable bearings the arm has, as well what is shape of the environment where it operates. The number of aspects of the problem you can vary largely independent of each other are the degrees of freedom of the problem. The values of these aspects are the independent variables. You can look at the problem as a space with each thing you vary as a different coordinate axis. The values that you cannot vary directly but are changed by changing the independent variables are the dependent variables. The dependent variables are then values of a function on the problem space that you are trying to optimize in some way. Sometimes people use degrees of freedom to refer to not just the number of independent variables, but also the number of different values for each variable. In real-world applications, a dimension is used to measure a particular kind of thing, such as time, distance, angle, or electrical charge, where one measurement class cannot be converted to another class, such kilograms to coulombs. Sometimes, like time and distance, it is discovered they can be converted, which leads to a deeper understanding of the real world. Each measurement class, such as distance, can be measured in a number of different units, such as meters, inches, furlongs, and parsecs. These different units can be converted one to others of the same kind, but not different classes. The units of measure are treated as if undefined variables which multiply the numerical measurement. Unit conversion can then be handled as multiplying and dividing related units. For example, 2 meters is 2 meters times 39.37 inches divided by 1 meter, which equals 78.74 inches. Dimensional or unit analysis is a technique of verifying the units of measures in various products correctly reflects the units used in factors. For example, electrical charge cannot be converted to time, so charge per second, or current, is irreducible. However, in current times potential difference, the charge unit is divided by itself and disappear. The result is power, which can also be expressed in non-electricity units such as joules per second.